You know the sun. Big, right? Obviously, enormous. It fits 1,000,000 Earths inside it and basically runs the entire solar system on its own gravitational personality. It's the baseline for everything we understand about life and light. But here's the thing. In stellar terms, our sun is a peppercorn. A literal peppercorn next to a football if you set it beside some of what's actually out there. And I'm not just being poetic. If you replaced our sun with a star like UY Scuti, the edge of that star wouldn't just swallow Earth. It would extend past the orbit of Jupiter. It would devour everything we have ever known as a species in a fraction of a second, and it still wouldn't be finished growing. We're starting here because the question of how big a star can actually get doesn't have a clean textbook answer. It has a limit, a hard physical ceiling. And some stars in our universe have apparently decided to ignore the rules entirely. Look, I thought I understood what large meant. We all do. We see the horizon, we see the mountains, we see the sun in the sky, and we feel small. But as you start to climb this ladder of stellar scale, that feeling of being small turns into a total collapse of perspective. It's a journey, a climb. And honestly, I'm still a little altitude sick from looking at the numbers. To understand how we get to the monsters, we have to start with the map everyone in astronomy uses but nobody really explains to the rest of us. The Hertzsprung-Russell diagram. Think of it as a map of a journey, not a dry chart. On one axis, you have how hot a star is. On the other, how bright it shines. It's a naming system that makes sense only if you already know what it means. O, B, A, F, G, K, M. But for our purposes, it's the trail map for our ascent. Our sun sits right in the middle. It's a G-type main sequence star. It's stable, it's predictable, and it's the benchmark. But the moment we step off that middle ground, things get weird fast. We move toward the massive B-type stars like Bellatrix in the constellation Orion. Bellatrix is roughly 8 times the mass of the sun. That doesn't sound like a jump from a peppercorn to a football yet, right? But Bellatrix is nearly 6 times the sun's radius. If the sun is a marble, Bellatrix is a basketball. And here's the thing. It's not just bigger, it's living faster. Because it's more massive, the gravity is crushing its core with such violence that it has to burn through its fuel at a terrifying rate just to stay inflated. While our sun will live for 10 billion years, a star like Bellatrix might only get a few tens of millions. It's a trade-off. To be big is to be brief. And if that's a massive main sequence star, what happens when you push the physics even further? You get to the O-type stars. These are the blue legends of the galaxy. Take a look at the R136A1. Seriously, that name sounds like a serial number, but it's a celestial violation. It shouldn't exist by the rules we thought we knew. For a long time, astronomers thought there was a hard limit of 150 times the mass of the sun. They figured any more than that, and the star's own radiation would literally blow it apart before it could even finish forming. But R136A1 is sitting there at roughly 200 to 250 times the mass of the sun. It's nearly 30 times the diameter of our sun. But its brightness is what actually breaks your brain. It is nearly 9 million times more luminous than the sun. Just let that sit for a second. If you took all the light the sun produces in a year, R136A1 produces that same amount of energy in about 4 seconds. It is a blowtorch in a universe of candles. But interestingly, R136A1 isn't the biggest star. It's the most massive, sure, but massive and big are two very different things in space. To find the truly largest things in the universe, we have to look at the dying. This is where the ascent gets steep. When a star like our sun runs out of hydrogen, it doesn't just go out, it panics. It starts fusing heavier elements, the core shrinks, the outer layers lose their grip, and the star swells. This is the red giant phase. When our sun does this in about 5 billion years, it will expand until it likely consumes Mercury and Venus. It might even swallow Earth. It will become a red giant, a bloated, ghostly version of its former self. Take a star like Mira A. It's a red giant that's actually pulsing. It grows and shrinks over the course of about 330 days. It's a star with a heartbeat. At its largest, it's hundreds of times the radius of the sun, but we're still in the foothills of this mountain. If your sense of scale has already collapsed and we're not even at the supergiants yet, stick around and hit subscribe. because we go this deep every week, climbing through these kinds of cosmic rabbit holes. Now, we reach the climax of the climb, the red supergiants. This is where physics starts to feel like science fiction. We start with Betelgeuse. You can see it tonight in Orion. It's that reddish-orange pinprick of light. If you replaced our sun with Betelgeuse, the surface of the star would stretch all the way out to the asteroid belt, maybe even as far as Jupiter. It's roughly 700 to 900 times the radius of the sun. It's so big that it's not even a solid sphere in the way we think of the sun. It's more like a boiling, turbulent nebula of plasma, shedding its mass into space like a giant dying animal. We've actually imaged the surface of Betelgeuse, one of the few stars we can see as more than just a dot, and it's lumpy. It's asymmetrical. It's a monster in the middle of a breakdown. But even Betelgeuse gets dwarfed. We keep climbing. We find UY Scuti. For a while, this was the undisputed heavyweight champion of the galaxy. It's a variable hypergiant with a radius roughly 1,700 times that of the sun. I know you're trying to picture this. Genuinely, good luck. 5 billion suns could fit inside the volume of UY Scuti. If you were in a racing jet traveling at the speed of sound, it would take you 200 years to fly around at once. And yet, despite its size, it's 40% cooler than our sun. It spread its heat so thin over such a massive surface area that it's actually quite chilly for a star. It's also nearly invisible to the naked eye because it's tucked away behind gas and dust 9,500 light-years away. Then there's WOH G64. This one is special because it's not even in our galaxy. It's in the Large Magellanic Cloud, a satellite galaxy orbiting the Milky Way. We've recently managed to image it with the Very Large Telescope Interferometer, and it's surrounded by a massive donut-shaped cocoon of dust. It might be 1,500 to 2,000 times the radius of the sun. We are talking about a star so large that its outer atmosphere is barely held on by gravity. It's essentially a cloud of fire the size of a solar system. At this point, you have to ask, okay, is there a ceiling? Can a star just keep getting bigger? And here's the thing. Physics finally says no. There is something called the Hayashi Limit. It's a theoretical line on the map we talked about earlier. As a star gets larger and cooler, its outer layers become incredibly unstable. If a star tries to grow past a certain point, roughly 2,500 times the radius of the sun, it becomes hydrostatically unstable. Its own convection, the way it moves heat from the core to the surface, starts working against it. The star literally cannot hold itself together anymore. It would begin to shed mass so fast that it would shrink back down or simply fall apart. So we think we've found the answer. The largest stars are likely right around that 1,500 to 2,000 solar radii mark. We are looking at the ceiling, but, and there's always a but in astronomy, our measurements are still a bit fuzzy. When you're looking at something 10,000 light-years away through a telescope, trying to figure out exactly where the surface of a glowing transparent cloud of gas begins is incredibly difficult. Some of these stars might be smaller than we think. Some might be even closer to the limit. There's a mix of intellectual humility and mounting awe that comes with this. I realize that saying 2,000 times the radius means almost nothing until you realize we're talking about a single object that could contain every planet, every asteroid, and every human being who has ever lived 1 billion times over with room to spare. It's a scale that feels like it shouldn't be allowed to exist in the same universe as us. And yet, it does. What's truly remarkable to me isn't just the size of these things, it's that we know they're there. We are these tiny creatures on a rocky planet orbiting a peppercorn of a star, and we built tools, mirrors and sensors and math to measure a monster on the other side of the galaxy. We can tell you its temperature. We can tell you what it's made of. We can tell you that it's dying, and that when it finally goes, it will leave behind a black hole or a neutron star that is the exact opposite. Something with the mass of a star crushed into the size of a city. We've reached the top of the climb, and the view is honestly a bit disorienting. We think we've found the largest stars, but the universe is large enough that there may be something bigger lurking in a galaxy we haven't peered into yet. Maybe there's a star out there right now, pushing against the Hayashi Limit, defying the math we've written down. Before we wrap, drop a comment. What's the thing about stellar scale that actually breaks your brain the most? Is it the volume, the lifespan, or just the fact that our sun is a speck? Because at the end of the day, These giants are just a reminder of the invisible structure beneath everything. The largest things in the universe are still subject to physics we can describe and diagram and name. The scale is a gift. It's a reminder that we live in a reality that is far more vast and far more violent than our daily lives suggest. But it's a reality that we are actually capable of understanding. We might be small, but our reach, our ability to see and measure the ceiling of the universe is anything but. Gone are the days when these were just points of light. Now they're worlds of fire, and we're just getting started with the map.